Hello there, friends. In this video, we're going to discover how quantum physics reveals what reality truly is. For the next few hours, we'll slowly walk you through the ideas that control the tiniest bits of matter in the universe, from how particles act like waves to how they connect with each other and more. Every chapter is made to teach you something amazing while you slowly fall asleep. So make yourself comfortable, let your mind relax, and allow the calm mysteries of the quantum universe to take you away. Chapter 1. What is quantum physics? Quantum physics is the area of science that tells us how the tiniest particles in the universe act. It shows us how atoms, electrons, photons, and other particles smaller than atoms interact, travel, and are. Unlike regular physics, which does a good job explaining everyday things like planets, cars, or even tiny grains of sand, quantum physics deals with things at the atomic and subatomic level, where the universe's rules work in completely strange ways. To really get quantum physics, it helps to know the history of why it was needed. At the start of the 1900s, physics was thought to be almost finished. The classic ideas like Newton's motion laws, Maxwell's electromagnetic equations, and the thermodynamics rules had explained nearly everything we could see in nature. Many people thought that all the big questions had answers, and only small details were left. But when scientists started looking closer at certain things, problems with the classical ideas began showing up. One of the first big issues came from studying blackbody radiation. A blackbody is an imaginary object that takes in all radiation and gives off energy only based on how hot it is. According to regular physics, the energy given off by a blackbody should grow without limit at shorter wavelengths, which led to what people called the ultraviolet catastrophe. But real experiments didn't show this. Instead, the energy given off reached a high point at a certain wavelength and then fell, something the old theory couldn't explain. In 1900, a German scientist named Max Planck came up with a brave answer. He said that energy isn't released in a smooth flow, but in separate chunks. These chunks, or quanta, created the foundation of a new thought that energy could only come in certain amounts. Planck brought in a constant to explain this connection, which we now call Planck's constant. His formula E equals hf showed energy as matching the frequency with h standing for this basic constant. Even though people first saw it as just a math trick, Planck's thought created the base for a new way to understand energy and light. A few years after that, Albert Einstein pushed Planck's thought even further when he studied the photoelectric effect. This happens when light touches a metal surface and makes it release electrons. Regular physics said that making light brighter should free more electrons no matter what the light's frequency was. But that's not what took place. Tests showed that only light over a certain frequency could make electrons come out no matter how strong the light was. Einstein explained this by saying that light itself is made of particles, which we now call photons, and that every photon held a certain amount of energy. If a photon didn't have enough energy, it couldn't knock an electron loose. This explanation proved Planck's quantum thought directly, and it got Einstein the Nobel Prize in 1921. The idea that light could act as both a particle and a wave felt very odd back then, but it turned out this wasn't just true for light. In 1924, a French scientist named Louis de Broglie suggested that matter might also show wave-like features. This thought, which started as guesswork, was later proven by tests showing that electrons could make interference patterns, things that people had only seen with waves when sent through a double-slit setup. This proved that all particles could show both wave and particle features depending on how they were looked at. With these findings, a new part of physics was starting, one that would need a total rethinking of nature's rules. Through the 1920s, scientists like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac built the math systems that would turn into quantum mechanics. Heisenberg's method, called matrix mechanics, looked at things you could measure and how they changed with time. Schrödinger brought in wave mechanics and the now famous wave function, a math picture of a quantum system's possible conditions. Dirac later mixed quantum theory with Einstein's special relativity and predicted that antimatter existed. Even though they seemed to take different paths, the various methods turned out to be the same, giving different ways to understand the same odd rules controlling the quantum world. Together, they made the structure of modern quantum mechanics. At the heart of this structure sits a group of ideas that go against our everyday experiences. In the quantum world, some physical features are quantized. They can only have certain separate values. For example, the energy levels of an electron in an atom are not smooth. An electron has to take in or give out a certain amount of energy to jump between levels. This is completely unlike what we see in the big world around us. Another key idea is superposition. In regular terms, a coin is either heads or tails. But in the quantum world, until we look at it, a system can be in a mix of many states. This isn't just because we don't know enough. It's a basic feature of the system. Only when we measure it does the system seem to pick one specific outcome. Even stranger is entanglement. When two particles get entangled, the state of one connects directly to the state of the other. It doesn't matter how far apart they are. Measuring one right away gives us information about the other. This strange link has been tested over and over and has always matched what quantum mechanics predicted. Another core thought is uncertainty. Werner Heisenberg came up with a rule showing that certain features like a particle's position and momentum can't both be known exactly at the same time. The more carefully one is measured, the less exactly the other can be known. This isn't because our tools aren't good enough. It's a built-in feature of quantum systems. To make guesses in quantum physics, scientists use wave functions, math tools that show the chance of finding a system in any given state. Unlike regular physics, which says definite results, quantum physics works with chances. When we measure a system, we get one result. But before that, only chances exist. Many tests have proven the rules of quantum mechanics very carefully. One of the most well-known is the double-slit experiment with electrons. When electrons are shot at a wall with two slits and nobody watches, they make an interference pattern showing wave action. But if we put detectors to see which slit each electron goes through, the pattern goes away and the electrons act like particles. This change based on watching is one of quantum physics' most puzzling and interesting features. Other tests like those checking Bell's inequalities have shown that entangled particles break the guesses of regular physics, proving quantum theory even more. Quantum tunneling, another proven thing, shows that particles can go through walls that should block them according to regular mechanics. This happens in the fusion reactions powering the sun, and it's used in tools like tunnel diodes. Quantum physics isn't only ideas, it's needed for much of today's technology. Transistors, the parts that make all computers and smartphones work, use the quantum action of electrons in semiconductors. Lasers work based on electrons jumping between quantized energy levels. Magnetic resonance imaging, or MRI, uses nuclear quantum features to make detailed pictures of the human body. Even future tools like quantum computers want to use things like superposition and entanglement to solve problems regular machines can't handle. All of this works because quantum physics correctly tells us how nature acts at its most basic level. It moves away from classical ideas, but gives them a set of rules that are not only steady and testable, but amazingly exact. These rules might seem weird, but they're the foundation that much of our modern world sits on. In short, quantum physics is the study of how the universe works at the smallest sizes. It came from needing to explain things that old theories couldn't. And it brought in ideas that challenge common sense but have passed the test of time through testing and use. Though it's abstract and often goes against intuition, quantum mechanics has become one of the most successful and life-changing frameworks in all of science. Chapter 2. Wave-particle duality. Wave-particle duality is one of the deepest and most surprising rules in quantum physics. It means that all particles, including light and matter, can show both wave-like and particle-like features depending on how they're watched. This idea changed our understanding of the physical world and marked a big turning point in how modern physics developed. The story starts with light. For hundreds of years, scientists argued about whether light was a wave or a particle. In the 1600s, Isaac Newton said that light was made of particles, which he called corpuscles. Around the same time, Dutch scientist Christian Huygens argued that light was a wave like ripples in water. These two competing ideas lived together for a long time, with test results supporting both at different points in history. In the 1800s, the wave idea gained strength. Tests by Thomas Young in 1801 showed that when light goes through two narrow slits and hits a screen, it makes a pattern of bright and dark bands. This is called an interference pattern and shows wave action. If light were just a stream of particles, it would make two bright spots behind the slits, not a detailed pattern. The wave model explained this perfectly, and for most of the 1800s, light was widely accepted as a wave. But the particle model of light came back with a twist in the early 1900s. In 1905, Albert Einstein explained the photoelectric effect, the thing that happens when light hitting a metal surface can push electrons out of it. Classical wave theory couldn't explain why light below a certain frequency, no matter how strong, didn't knock electrons loose. Einstein said that light comes in separate packets or quanta, now called photons. Each photon carries energy matching its frequency. If the photon's energy isn't high enough, it can't push an electron out no matter how many photons are there. This could only be explained if light had particle-like features. These two conflicting actions, wave-like interference and particle-like quantization, both seemed real. This was the first clear sign that the old categories of wave and particle weren't enough anymore. Then came the amazing idea that wave-particle duality might not just apply to light, but to matter too. In 1924, French scientist Louis de Broglie said that electrons, which people firmly believed were particles, might also show wave-like features. He suggested that every particle with momentum has a related wavelength, now called the de Broglie wavelength. Though the idea was unusual, it had deep theory implications and opened the door to a unified view of matter and energy. In 1927, this idea was tested by Clinton Davison and Lester Germer in the United States. They saw that a beam of electrons bouncing off a crystal of nickel made a diffraction pattern just like X-rays or visible light. This was final proof that electrons could act as waves. Around the same time, similar tests by George Thomson, son of J.J. Thomson who had found the electron, proved the same result. The dual nature of matter was no longer just theory, it was something you could see. This finding was revolutionary. Electrons, thought before to be point-like particles, could act like waves under the right conditions. These weren't comparisons or rough guesses. The wave action was real and measurable. The meaning was deep. It showed that all matter has a dual character, and what we see depends on how we see it. One of the strongest showings of wave-particle duality is the double-slit experiment. In this setup, a beam of particles like photons, electrons, or even bigger molecules is aimed at a wall with two slits. Behind the wall is a detection screen. If one slit is open, particles go through and make a single band. If both slits are open and nobody watches which slit each particle goes through, an interference pattern shows up, pointing to wave-like action. But if a detector is placed to watch which slit each particle goes through, the interference pattern goes away, and the particles make two separate bands as if they were little bullets. This change in result, depending only on whether measurement happens or not, is a key feature of quantum mechanics. It challenges the idea that particles have set paths or features before we measure them. Instead, it suggests that the act of watching plays a role in deciding how the system acts. The action of quantum objects is shown mathematically by wave functions. These wave functions spread out over space and show the chance distribution of finding a particle in a certain spot. The wave function changes according to Schrödinger's equation, a central formula in quantum mechanics. When no measurement happens, the particle's position is spread across many options. When a measurement happens, the wave function collapses and the particle shows up in one spot. This chance nature of quantum systems isn't because of test problems or lack of knowledge. It's built into the math and action of the system. Even with perfect information about the wave function, you can't predict with certainty the exact result of a single test. Only the chances are known ahead of time. This dual nature applies not just to electrons or photons, but to all particles. In recent decades, scientists have shown interference patterns using whole atoms and even large molecules made of dozens of atoms. These results show that wave-particle duality is a general feature of nature, not limited to light or small particles. The bigger the object, the shorter its wavelength, which is why everyday objects don't show noticeable wave action. The wavelengths of big objects are so tiny that they become nothing for practical reasons. Despite its abstract nature, wave-particle duality has practical results. It's needed for understanding the structure of atoms, how electrons act in solids, and the systems behind tools like electron microscopes and semiconductor devices. In electron microscopes, the wave nature of electrons lets scientists reach resolutions far beyond those of regular light microscopes, showing structures at the nanometer level. Wave-particle duality also sits at the heart of quantum field theory, the framework that mixes quantum mechanics with special relativity. In this theory, particles are seen as excitations or quanta of underlying fields that fill space. These fields vibrate and interact, and the resulting things are read as particles. In this sense, particles are localized expressions of field waves, strengthening the duality in a more modern form. Understanding wave-particle duality has made physicists give up classical thinking and accept a more complex but accurate description of the universe. Rather than asking whether something is a particle or a wave, quantum physics teaches us that those labels are limited and depend on context. What matters is the system's action under specific conditions and how we choose to measure it. This rule doesn't show a flaw in our logic or tests, but rather shows a deeper layer of reality that becomes visible only at very small sizes. Wave-particle duality isn't a contradiction. It's a broader understanding that nature doesn't fit neatly into classical boxes. Instead, it follows its own rules, and those rules become visible when we ask the right questions in the right ways. Even though this action might seem strange compared to the stability of the big world, it makes the foundation for all matter, energy, and interaction. Every atom in your body, every beam of light you've ever seen, and every material object around you owes its features to this quantum duality. It's one of the most tested, proven, and powerful thoughts in all of physics. By showing that things can act like both waves and particles depending on how we watch them, wave-particle duality changed science. It opened new paths for research and innovation, and gave us tools to explore nature at its most basic level. In doing so, it keeps guiding both theory research and practical technology, even a century after its finding. Chapter 3. The Uncertainty Principle. The uncertainty principle is one of the most well-known and basic parts of quantum physics. It totally reshapes how we think about measurement, exactness, and the very nature of physical reality at microscopic sizes. First worked out by German scientist Werner Heisenberg in 1927, the uncertainty principle shows a limit on how exactly we can know certain pairs of physical features of a quantum system at the same time. It's not just a technical problem with instruments, but a built-in feature of how nature works at the smallest sizes. At its core, the uncertainty principle tells us that there's a trade-off in how exactly we can measure two related amounts. The most commonly talked about example is the connection between a particle's position and its momentum. Momentum is mass times velocity, and in classical mechanics, both position and momentum can be measured with perfect precision if we use good enough instruments. But quantum mechanics brings in a different framework. One where particles are shown not by exact locations and speeds, but by wave functions, math descriptions that show probabilities. The wave function for a quantum particle like an electron spreads out in space. It tells us where the particle is likely to be found if we do a measurement, but it doesn't give an exact location until that measurement actually happens. The wider the wave function in space, the more uncertain the particle's position. On the other hand, if the wave function is narrow and bunched up in space, showing a well-known position, then its spread in momentum gets larger. This opposite connection between the spread in position and the spread in momentum is exactly what the uncertainty principle describes. The formal expression of Heisenberg's rule is often written as an inequality. The product of the uncertainties in position and momentum must be greater than or equal to a small constant. That constant is Planck's reduced constant divided by 2 pi. Mathematically, it's stated as deltax times delta greater than or equal to letter 210f/2, where deltax is the uncertainty in position and delta is the uncertainty in momentum. This means that the more exactly we try to figure out a particle's position, the less exactly we can know its momentum, and the other way around. This connection isn't because of problems with our equipment. Even with perfect detectors and zero test error, the uncertainty principle still applies. It's a direct result of the wave-like nature of particles. To understand why, think about a basic wave. A single frequency wave goes on forever in space. It has a very well-defined wavelength and therefore a very well-defined momentum. But because it's spread out evenly, it has no specific location. It's completely delocalized. On the other hand, to put a wave in a specific spot in space to make a wave packet that has a certain position, you have to combine many different frequencies. The result is a superposition of waves with slightly different momenta, leading to a wave packet that's located but uncertain in momentum. This trade-off isn't limited to position and momentum. The uncertainty principle applies to other pairs of amounts as well, like energy and time, or angular momentum and direction. In each case, there's a basic limit to how exactly both features can be known at the same time. These connections are all based in the math structure of quantum mechanics, especially in the way operators, math tools that stand for things you can observe, don't commute when used in different orders. One of the most important results of the uncertainty principle is that it breaks down the classical idea of determinism. In Newton's physics, if we know the position and momentum of every particle in a system, we can in theory predict the future state of the system with perfect accuracy. But in quantum mechanics, such complete knowledge is impossible. We can only speak in terms of chances and likelihoods, not certainties. The future isn't fixed, but controlled by chance distributions that come from the wave function. This rule also has deep meanings for our understanding of what it means to watch or measure something. In classical science, measurement is passive. We look at a system, and our watching shows features that were already there. In quantum mechanics, however, measurement is an active process that changes the state of the system. The uncertainty principle makes sure that the more we try to pin down one feature, the more we disturb its partner feature. One famous thought test that shows this is Heisenberg's microscope. Imagine trying to see an electron using a microscope that uses light. To get a clear image, we might try to use high-energy photons with short wavelengths. These would let us see small details and figure out the electron's position more exactly. But the high-energy photon would also give a large amount of momentum to the electron when they interact, disturbing its velocity. If we use lower-energy photons to avoid disturbing the electron's momentum, the long wavelength of the light blurs our image and makes the position less exact. This problem shows the unavoidable trade-off between knowing position and knowing momentum. In practical terms, the uncertainty principle sets hard limits on what we can know about systems like atoms, molecules, and subatomic particles. For example, it explains why electrons in atoms don't simply spiral into the nucleus. If an electron were trapped in an extremely small area near the nucleus, its position would be very well defined, but its momentum and thus its kinetic energy would have to be extremely large, making such a state unstable. Instead, electrons live in areas of space called orbitals, which show the chance distributions of where an electron might be found. These orbitals are stable because of the delicate balance enforced by the uncertainty principle. The uncertainty principle is also needed to understand the idea of zero-point energy, the thought that quantum systems never come completely to rest even at absolute zero temperature. A quantum harmonic oscillator, like a vibrating atom in a crystal lattice, keeps a minimum amount of energy because of the limits of the uncertainty principle. If it had zero energy, its position and momentum would both be exactly known, which the rule forbids. This leftover energy is an unavoidable result of the quantum rules. In particle physics, the uncertainty principle gives insight into the brief nature of certain particles and things. For instance, virtual particles which briefly pop in and out of existence in quantum field theory are allowed to break conservation of energy for very short times, something allowed by the time-energy form of the uncertainty principle. These virtual particles add to things you can see like the Lamb shift in atomic energy levels and the Casimir effect between closely spaced plates. Though these meanings may seem abstract, the uncertainty principle has very real and measurable results. Its predictions have been proven in countless tests across decades of research. It plays a central role in quantum optics, where the handling of light at the quantum level needs exact control over partner variables like phase and amplitude. It also affects precision metrology, the science of making extremely accurate measurements, by defining the ultimate sensitivity limits for instruments like atomic clocks and gravitational wave detectors. Understanding the uncertainty principle needs a shift in view. In the classical world, it makes sense to imagine that particles have exact positions and velocities at all times, even if we don't know them. But quantum physics makes us accept a new kind of knowledge, one that's naturally probabilistic and based on what can and can't be known at the same time. This doesn't mean that the quantum world is chaotic or ill-defined. On the contrary, it follows strict rules and gives exact statistical predictions. But those predictions concern distributions and likelihoods, not fixed results. The uncertainty principle isn't a failure of measurement. It's not a technological limit. It's a basic feature of how nature works. It's built into the math of quantum theory and supported by a century of test validation. Rather than thinking of it as an obstacle, physicists have welcomed it as a guide, a rule that shapes everything from the stability of atoms to the action of black holes. Even though the rule applies at sizes far smaller than everyday life, it underlies the action of all matter and energy. It explains why the atomic world is structured the way it is, why electrons take up specific energy levels, why chemical bonds form, and why the universe isn't frozen into deterministic predictability. It brings in a kind of built-in fuzziness to reality, a reminder that even the most basic amounts in the universe come with a degree of natural variability. In the vast landscape of physics, the uncertainty principle stands as a quiet but powerful reminder that knowledge itself has limits. And within those limits, new insights arise, not from being able to know everything, but from understanding the boundaries of what can be known. Chapter 4: Quantum Superposition. Quantum superposition is one of the most crucial and puzzling ideas in quantum physics. It means that a quantum system can be in many possible states at the same time, and that only through watching does the system settle into a single definite result. This rule isn't just theory. It's been seen in countless tests and is central to how particles, atoms, and molecules act at the smallest sizes. Yet it goes against our common sense understanding of the world, where things seem to be in one state or another, not both at once. In classical physics, an object can be in only one state at a given time. A ball is either on the left side of a table or the right. A switch is either on or off. This is how we're used to thinking about the world in terms of clear, definite conditions. But in the quantum realm, the action of particles is controlled by wave functions which show the chances of different results. Until a measurement happens, the system isn't in one of those results. It's in all of them at once in a superposition. To understand superposition, it helps to think about how particles act as waves. In quantum mechanics, particles like electrons, photons, or atoms are linked with wave functions. These wave functions aren't physical waves like water or sound, but math functions that show the likelihood of finding the particle in various states. When a particle can be in more than one state, its total wave function is made by adding together the wave functions of all those states. This addition isn't random mixing, but a coherent sum where the individual parts interfere with each other, much like overlapping ripples on a pond. The result of this addition is a new wave function that reflects the superposition of all possible states the particle could take up. For example, if an electron can be in location A or location B, its wave function might include both locations. Before any watching happens, the electron isn't just possibly in either A or B, it's truly in both, shown by a wave function that includes both options at the same time. The chances of finding the particle in either location become real only when a measurement happens, making the wave function collapse into one result. One of the most well-known examples of superposition is the famous thought test called Schrödinger's cat, made up by Austrian scientist Erwin Schrödinger in 1935. The test describes a made-up scenario where a cat is placed in a sealed box with a device that has a 50% chance of releasing poison depending on the decay of a radioactive atom. According to quantum theory, until the box is opened and the system is watched, the atom is in a superposition of decayed and undecayed states. As a result, the cat is thought to be both alive and dead, not in the sense of being partly alive, but in the sense of being in both states at the same time. The point of Schrödinger's thought test was to highlight the strangeness of using quantum rules to big objects. In practice, quantum superposition is hard to see directly at large sizes because bigger systems quickly interact with their surroundings in a process called decoherence. This process makes the system lose its quantum coherence and act more classically. But at small sizes like individual atoms, electrons, or photons, superposition is not only real but measurable. Tests have repeatedly proven the existence of superposition. In one example, scientists send individual electrons through a pair of slits in a wall. If no measurement happens to figure out which slit the electron goes through, the electron acts as though it goes through both slits at the same time, making an interference pattern on a screen. This pattern is the result of the electron's wave function being in a superposition of went through slit A and went through slit B. Only when detectors are placed to watch the path does the interference disappear, and the electron acts like a classical particle that went through one slit or the other. Superposition isn't limited to position. Quantum systems can be in superpositions of other features like spin, polarization, or energy levels. For instance, the spin of an electron, a quantum version of angular momentum, can point in different directions. Until it's measured, the spin is in a superposition of up and down. Once measured, the spin takes on a definite value. Before measurement, however, the particle's spin is in a genuine quantum mixture of both options. This rule is also used in tests with photons where the polarization, the direction of the light's electric field, can be in a superposition of horizontal and vertical states. When passed through special devices like beam splitters or polarizers, the photons show interference effects that prove the presence of superposition. These actions aren't mere quirks of theory. They're tested and proven and mathematically predictable. Quantum computers rely heavily on the rule of superposition. Unlike classical computers, which use bits that can be in one of two states, 0 or 1, quantum computers use quantum bits or qubits, which can be in superpositions of both 0 and 1 at the same time. This lets quantum computers do certain calculations much more efficiently than classical machines, by processing many options in parallel. However, keeping superposition in qubits is a major technical challenge, as they're extremely sensitive to noise and environmental interactions that cause decoherence. The thing of superposition also plays a role in quantum chemistry and atomic physics. Electrons in atoms are shown by wave functions that make standing wave patterns around the nucleus. These standing waves stand for superpositions of possible positions and energies. The shapes and interactions of these wave functions decide how atoms bond with each other and make molecules. In chemical reactions, the transition states between reactants and products often involve superpositions of different bonding arrangements. Superposition isn't simply a curiosity. It's at the heart of why quantum systems act differently from classical ones. It brings in the idea that particles don't have definite features until those features are watched. This leads to questions about the nature of measurement, the role of observers, and the completeness of quantum theory. While these questions have sparked debate and various readings of quantum mechanics, the physical reality of superposition has never been in doubt. Physicists have also explored superposition using increasingly large systems. In recent years, researchers have managed to place small molecules consisting of dozens or even hundreds of atoms into superposition states. These tests push the boundaries of how large a system can be while still showing quantum action. Each new result gives stronger evidence that superposition isn't limited to the microscopic world, although keeping coherence becomes exponentially harder as the system grows. Despite its strangeness, the math of superposition is exact and reliable. The wave function that shows a quantum system changes deterministically according to Schrödinger's equation until a measurement happens. This change preserves the superposed states and lets interference patterns show up. The predictive power of this math has been proven across countless tests and underlies much of modern quantum theory. Understanding superposition needs letting go of the idea that physical systems must always be in definite observable states. In the quantum world, potentialities exist together until the act of measurement reduces them to actualities. It's not that we simply don't know what state the system is in. Rather, the system truly is in all its allowed states at once, each with a certain amplitude and phase that affect how it combines with others. The meanings of this idea are vast. It suggests a level of indeterminacy in nature that isn't because of ignorance or chaos, but is part of the fabric of reality. At the same time, superposition offers powerful tools for technology and scientific understanding. It enables precision control in fields like quantum optics and quantum information, and it plays a central role in the structure and action of atoms, molecules, and materials. The rule of superposition has been with quantum mechanics since its start and continues to be one of the most fascinating and tested aspects of the theory. It shows that the quantum world is richer and more complex than the classical one we see every day. In that richness lies both mystery and possibility. A framework that not only explains how particles act, but also offers the foundation for some of the most advanced and promising technologies of the future. Chapter 5. Quantum Entanglement. Quantum entanglement is one of the most fascinating and tested things in modern physics. It describes a situation where two or more quantum particles become linked in such a way that the state of one particle can't be described separately from the state of the other no matter how far apart they are. This connection stays even when the entangled particles are separated by huge distances. What happens to one right away affects the other not through any signal or force that travels between them, but as a result of the math controlling their shared quantum state. The idea of entanglement comes naturally from the rules of quantum mechanics, especially the thought of superposition. When two quantum systems interact and then separate, their wave functions can become entangled, meaning that their chances are no longer independent. Instead, they're shown by a single combined wave function that holds correlations between the particles. These correlations remain even when the particles are no longer in contact. To understand how entanglement works, it helps to think about a simple example involving particle spin. Spin is a basic quantum feature similar to angular momentum. For electrons, spin can take one of two values up or down. If two electrons interact in such a way that they must have opposite spins, their total spin state becomes entangled. This means that if one is measured and found to be spin up, the other will be spin down and the other way around. But until a measurement happens, neither electron has a definite spin. Instead, they exist in a superposition of both options and the results are strictly correlated. This entangled state doesn't depend on the distance between the particles. If one electron is sent to one side of the universe and the other to the opposite side, measuring the spin of one still decides the spin of the other instantly. This feature confused even the founders of quantum theory. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a paper arguing that such action meant that quantum mechanics was incomplete. They suggested that there must be hidden variables, unknown factors that predetermine the result of each measurement. Einstein famously called entanglement spooky action at a distance, expressing discomfort with the idea that one particle could instantly influence another. This led to the making of what became known as the EPR paradox, named after the authors of the paper. The paradox pointed out that if quantum mechanics were correct, it allowed for non-local effects, influences that traveled faster than light, seemingly breaking the rule of causality. For decades, this question stayed unresolved. Could there be hidden variables underlying quantum action, or was the theory truly non-local in the way it seemed to be? In the 1960s, physicist John Bell came up with a way to test these competing ideas. He developed what are now called Bell inequalities, math relationships that would be satisfied if hidden variables controlled the results of measurements. But if entanglement acted according to quantum mechanics, these inequalities would be violated. Bell's work gave a clear experimental test that could distinguish between the two possibilities. Starting in the 1970s and continuing through decades of research, numerous experiments tested Bell's inequalities using pairs of entangled photons, electrons, and other particles. The results were consistent and clear. The inequalities were violated in exactly the way quantum mechanics predicted. There were no hidden variables. The correlations between entangled particles were real, instant, and non-local. These findings have been confirmed with increasing precision and under increasingly strict conditions, leaving little room for doubt. One of the most famous experiments was carried out by Alain Aspect and his team in France in the early 1980s. They used pairs of entangled photons and measured their polarizations at different angles. The results matched quantum predictions and violated Bell's inequalities. More recent experiments have closed various loopholes and confirmed the results with even greater certainty. The 2022 Nobel Prize in Physics was awarded to Aspect, John Clauser, and Anton Zeilinger for their pioneering work on entanglement and tests of Bell's inequalities. Entanglement is not limited to pairs of particles. Systems involving 3 or more particles can also become entangled, creating even more complex correlations. These multi-particle entangled states are called GHZ states or W states, depending on their structure. They have been created in laboratories and are being studied for their potential use in quantum technologies. The instant nature of entanglement does not allow for faster-than-light communication. While measuring one particle instantly affects the state of its entangled partner, the result of any single measurement appears random. Only by comparing measurements on both particles can the correlation be seen. This comparison requires classical communication, which is limited by the speed of light. So, while entanglement is non-local, it does not violate relativity. Despite its strangeness, entanglement has practical uses. One of the most promising is quantum communication. Entangled particles can be used to create secure communication channels through a process called quantum key distribution. In this method, any attempt to intercept or measure the transmitted information disturbs the entangled state and can be detected. This makes it possible to create communication systems that are fundamentally secure against eavesdropping. Entanglement also plays a key role in quantum computing. Quantum algorithms take advantage of entangled states to perform calculations that would be impossible or extremely slow on classical computers. Entanglement allows qubits to be correlated in ways that enable parallel processing of information across many possible states at once. This is one of the main reasons why quantum computers have the potential to solve certain problems much faster than traditional machines. Another use of entanglement is in quantum teleportation. This is not the science fiction idea of transporting matter instantly, but rather a method of transferring the quantum state of one particle to another distant particle using entanglement and classical communication. The original particle state is destroyed in the process, and the distant particle takes on that exact state. Quantum teleportation has been successfully demonstrated in laboratories over distances of hundreds of kilometers and is a building block for future quantum networks. Entanglement also has uses in precision measurement. By entangling particles used in sensors, scientists can achieve levels of sensitivity beyond what is possible with classical methods. This has uses in fields like gravitational wave detection, atomic clocks, and imaging technologies. Entangled photons are being used to improve the resolution and accuracy of measurements in ways that were not possible before. The study of entanglement continues to reveal new insights into the nature of quantum mechanics. It raises deep questions about the structure of space and time, the nature of information, and the limits of what can be known. Some physicists believe that entanglement may be a key to understanding the connection between quantum mechanics and gravity, two areas of physics that have not yet been fully unified. Entanglement also challenges our ideas about locality and separability. In classical physics, objects are distinct and separate. What happens to one object does not instantly affect another unless there is some physical interaction or signal between them. But entanglement shows that quantum systems do not always behave this way. Two particles can be connected in a way that transcends physical separation, forming a single system even when far apart. Philosophers and physicists have debated the meaning of entanglement since it was first proposed. Some see it as evidence that the universe is fundamentally interconnected at a deep level. Others view it as simply a feature of the mathematical structure of quantum mechanics without deeper metaphysical meaning. Regardless of interpretation, the experimental reality of entanglement is undeniable. Entanglement has been observed in systems ranging from photons and electrons to atoms, ions, and even small mechanical oscillators. It is a universal feature of quantum systems, not limited to any particular type of particle or interaction. This universality strengthens the case that entanglement is a basic property of nature. In summary, quantum entanglement is a proven and powerful aspect of quantum mechanics. It describes correlations between particles that cannot be explained by classical physics and that remain intact regardless of distance. These correlations have been tested extensively and have always agreed with the predictions of quantum theory. Entanglement is not just a theoretical curiosity, but a practical resource that is being used to develop new technologies in communication, computing, and measurement. It stands as one of the most striking examples of how the quantum world differs from our everyday experience. Chapter 6. The Observer Effect. The observer effect is one of the most debated and misunderstood concepts in quantum physics. It refers to the fact that the act of measuring or observing a quantum system can change the state of that system. This is not simply a matter of clumsy instruments disturbing delicate particles. Rather, it is a basic feature of quantum mechanics that arises from the nature of measurement itself and the way quantum systems are described mathematically. In classical physics, observation is thought to be passive. When we look at a planet through a telescope or measure the temperature of water with a thermometer, we assume that the act of measurement reveals properties that were already there. The planet's position and the water's temperature exist independently of whether we measure them. Measurement might introduce small errors or disturbances, but in principle, those could be minimized with better tools. Quantum mechanics changes this picture. In the quantum world, particles do not have definite properties until those properties are measured. Before measurement, a quantum system is described by a wave function, which contains information about all possible outcomes of a measurement and their probabilities. The system exists in a superposition of many possible states. When a measurement is made, the wave function collapses, and the system adopts one specific outcome. This collapse is sudden and depends on the type of measurement being performed. The classic example that shows the observer effect is the double-slit experiment. When particles like electrons or photons are sent through two slits without any observation of which slit they pass through, they create an interference pattern on a detection screen. This pattern is characteristic of waves and shows that each particle seems to go through both slits at once. However, if detectors are placed at the slits to determine which path each particle takes, the interference pattern disappears. The particles then behave like classical objects, going through one slit or the other, but not both. The change in behavior is not due to the physical impact of the detectors. Even very gentle measurements that transfer minimal energy to the particles produce the same effect. What matters is whether the information about the particle's path is available in principle, not whether a human being actually looks at the data. This has led to careful thinking about what constitutes an observer in quantum mechanics. An observer in quantum mechanics does not need to be a conscious person. Any interaction that extracts information from a quantum system and records it in a way that could be retrieved later counts as an observation. This could be a detector, a piece of measuring equipment, or even an interaction with the environment. The key factor is that the information becomes entangled with something outside the quantum system, causing the wave function to collapse or the system to decohere. The idea of wave function collapse has been a source of controversy since the early days of quantum mechanics. The wave function evolves smoothly and predictably according to Schrödinger's equation when no measurement is taking place. But when a measurement occurs, the evolution suddenly changes. The system jumps to one of the possible outcomes, and the smooth evolution is interrupted. This jump is not described by Schrödinger's equation, and there is no agreed-upon explanation for exactly how or why it happens. Different interpretations of quantum mechanics offer different answers to this problem. The Copenhagen interpretation, developed by Niels Bohr, Werner Heisenberg, and others, treats measurement as a fundamental process that lies outside the usual rules of quantum mechanics. According to this view, the wave function is just a tool for calculating probabilities, and it does not represent physical reality. When a measurement occurs, the wave function collapses, and one outcome is realized. Other interpretations take different approaches. The many worlds interpretation, proposed by Hugh Everett in the 1950s, suggests that the wave function never collapses. Instead, every possible outcome of a measurement actually happens, but in separate branches of a vast multiverse. When we perform a measurement, the universe splits, and we experience only one branch while other versions of us experience other branches. In this view, there is no observer effect in the traditional sense because all outcomes occur. The pilot wave theory, also known as Bohmian mechanics, takes yet another approach. It suggests that particles always have definite positions and velocities, guided by a pilot wave that evolves according to Schrödinger's equation. Measurement reveals these pre-existing properties rather than creating them. The apparent randomness and observer effect arise from our incomplete knowledge of the initial conditions, not from any fundamental indeterminacy in nature. Despite these differing interpretations, the experimental predictions of quantum mechanics are the same regardless of which interpretation one prefers. All interpretations agree on what will be observed in any given experiment. The differences lie in the underlying story about what is happening and what is real. The observer effect has practical consequences for experiments and technology. In quantum computing, maintaining the delicate superposition states of qubits requires isolating them from any external observation or interaction that might cause decoherence. Even tiny interactions with stray photons, vibrations, or electromagnetic fields can act as measurements and destroy the quantum state. This is why quantum computers must be operated at extremely low temperatures and carefully shielded from their environment. In quantum cryptography, the observer effect provides a way to detect eavesdropping. If an unauthorized party tries to intercept and measure quantum information being transmitted, their measurement will disturb the quantum state and introduce detectable errors. This allows the legitimate users to know that their communication has been compromised. The observer effect also plays a role in fundamental limits on measurement precision. Heisenberg's uncertainty principle is closely related to the observer effect. The more precisely we try to measure one property of a quantum system, the more we disturb its complementary property. This is not just a limitation of our tools, but a consequence of how quantum systems respond to measurement. Recent experiments have explored the observer effect in increasingly sophisticated ways. Researchers have developed techniques for weak measurement, where the system is measured gently enough that the wave function is only partially collapsed. This allows information to be extracted while preserving some quantum properties. Other experiments have used quantum erasers, devices that can reverse the effects of a measurement under certain conditions and restore interference patterns. One striking demonstration is the delayed choice quantum eraser experiment. In this setup, the decision of whether to measure which path a particle took can be made after the particle has already passed through the slits. Surprisingly, the presence or absence of which path information affects the interference pattern retroactively. This suggests that the act of measurement is not localized in time in the way we might expect and raises deep questions about causality and the nature of time in quantum mechanics. The observer effect reminds us that in quantum mechanics, the boundary between the observer and the observed is not as clear as it is in classical physics. Measurement is not a passive act of revealing pre-existing properties, but an active process that shapes the state of the system. This has profound implications for how we think about reality and knowledge. Some have speculated that consciousness plays a special role in quantum measurement, but this view is not widely accepted among physicists. The overwhelming evidence suggests that any physical interaction that extracts and records information is sufficient to cause wave function collapse or decoherence, regardless of whether a conscious being is involved. The observer effect continues to be a topic of research and debate. It touches on fundamental questions about the nature of reality, the role of information, and the limits of what can be known. While the practical consequences are well understood and applied in technology, the deeper meaning remains an open question that challenges our understanding of the universe. Chapter 7: Quantum Tunneling. Quantum tunneling is one of the most remarkable and counterintuitive phenomena in quantum physics. It describes the ability of particles to pass through barriers that, according to classical physics, they should not be able to cross. This happens because particles at the quantum level are described by wave functions that can extend beyond physical obstacles, allowing for a small but non-zero probability of the particle appearing on the other side of a barrier. In classical mechanics, if a ball is rolled toward a hill, it will only make it over the top if it has enough energy to reach that height. If its energy is too low, it will roll partway up and then come back down. There is no way for the ball to appear on the other side of the hill without having enough energy to go over the top. This is the behavior we expect from everyday objects, and it follows directly from the conservation of energy. But quantum mechanics introduces a different possibility. A quantum particle approaching a barrier that it does not have enough energy to cross can still sometimes be found on the other side. This does not mean the particle gained extra energy or somehow climbed over the barrier. Instead, the particle's wave function extends into and through the barrier region, and there is a probability that the particle will be detected on the far side. This process is called quantum tunneling. The mathematics of tunneling comes from solving Schrödinger's equation for a particle encountering a potential barrier. The wave function does not drop to zero at the barrier. Instead, it decays exponentially inside the barrier but remains non-zero. If the barrier is thin enough, the wave function can extend to the other side, meaning there is a finite probability of finding the particle there. The probability of tunneling depends on the height and width of the barrier and the energy of the particle. Higher barriers and wider barriers make tunneling less likely, but it never becomes completely impossible unless the barrier is infinitely high or wide. Quantum tunneling was first recognized as a key process in explaining radioactive decay. In the 1920s, physicists were puzzled by alpha decay, the process by which certain atomic nuclei emit alpha particles. These alpha particles are trapped inside the nucleus by a strong force, and according to classical physics, they do not have enough energy to escape. Yet, they do escape, and they do so at measurable and predictable rates. George Gamow, along with Ronald Gurney and Edward Condon, independently explained this process using quantum tunneling in 1928. The alpha particle inside the nucleus is trapped by a potential barrier created by the strong nuclear force. Even though the particle does not have enough energy to overcome this barrier classically, its wave function allows for a small probability of tunneling through. Over time, this probability results in the emission of alpha particles, which we observe as radioactive decay. Tunneling is also essential to the process of nuclear fusion in stars. In the core of the Sun, hydrogen nuclei fuse to form helium, releasing enormous amounts of energy. For fusion to occur, the nuclei must come close enough for the strong nuclear force to bind them together. But they are both positively charged and repel each other with great force. The temperature and pressure in the Sun's core provide some of the energy needed to overcome this repulsion, but it is not enough on its own. Quantum tunneling allows the nuclei to get close enough to fuse even when they do not have sufficient energy classically. Without tunneling, stars like the Sun would not shine. Quantum tunneling is not limited to nuclear processes. It plays a role in many areas of chemistry and material science. For example, tunneling affects the rates of certain chemical reactions, particularly those involving the transfer of protons or electrons. Enzymes in biological systems sometimes rely on tunneling to speed up reactions that would otherwise be too slow to sustain life. In solid-state physics, tunneling is the basis for many technologies. Tunnel diodes are electronic components that use quantum tunneling to allow current to flow in ways that ordinary diodes cannot. These devices can operate at very high speeds and are used in specialized applications like microwave circuits and oscillators. Scanning tunneling microscopes, or STMs, use quantum tunneling to create images of surfaces at the atomic level. A sharp metal tip is brought very close to a surface without touching it. A voltage is applied, and electrons tunnel between the tip and the surface. The tunneling current is extremely sensitive to the distance between the tip and the surface, allowing the microscope to map out the positions of individual atoms. The STM was invented in 1981 by Gerd Binnig and Heinrich Rohrer, who were awarded the Nobel Prize in Physics in 1986 for their work. This tool has been essential for advances in nanotechnology and material science. Flash memory, used in USB drives and solid-state hard drives, relies on quantum tunneling. Data is stored by trapping electrons in tiny cells. To write or erase data, electrons are made to tunnel through a thin insulating barrier into or out of the storage cell. This process is controlled by applying voltages, and it allows for fast and reliable data storage. Tunneling also appears in the phenomenon of electron tunneling in molecules. In systems where electrons are confined to certain regions, there is a probability that they will tunnel to other regions even if separated by barriers. This affects the electrical and optical properties of molecules and materials, and is important in understanding conductivity, superconductivity, and other electronic behaviors. One of the most interesting aspects of tunneling is that it happens instantaneously, in the sense that the particle does not spend time traveling through the barrier. Experiments have measured tunneling times and found them to be extremely short, often indistinguishable from zero within the limits of measurement. This raises questions about the nature of time and causality at quantum scales, though it does not violate relativity because no information or energy is transmitted faster than light. Quantum tunneling is also being explored for future technologies. Researchers are investigating the use of tunneling in quantum sensors, which could detect tiny changes in magnetic or electric fields with unprecedented sensitivity. Tunneling is also relevant to the development of quantum computers, where precise control of quantum states involves understanding and managing tunneling processes in engineered systems. Despite its wide range of applications, tunneling remains a deeply quantum phenomenon that has no classical analogy. It is a direct consequence of the wave nature of particles and the probabilistic interpretation of the wave function. Tunneling shows that the boundaries we think of as solid and impenetrable at the macroscopic level are in fact permeable at the quantum level. Quantum tunneling has been confirmed through countless experiments and observations across many fields of physics and chemistry. It is one of the clearest demonstrations that the rules governing the microscopic world are fundamentally different from those we experience in everyday life. Tunneling is not a rare or exotic occurrence, but a common and essential process that shapes the behavior of atoms, molecules, and subatomic particles throughout the universe. Chapter 8. The role of probability. Probability is at the very heart of quantum physics. Unlike classical mechanics, which allows us to predict the exact future state of a system if we know its present condition, quantum mechanics deals with likelihoods and uncertainties. This shift from certainty to probability is not due to a lack of information or imperfect measurements. It is a fundamental characteristic of how nature operates at the smallest scales. In classical physics, if we know the position and velocity of a particle, we can use Newton's laws to calculate exactly where it will be at any future time. The outcome is determined, and probability only enters when we lack complete information. For example, when flipping a coin, we use probability because we cannot track all the forces and motions precisely enough. But in principle, the result is determined by the initial conditions. Quantum mechanics is different. Even with complete knowledge of a quantum system state, we cannot predict with certainty the outcome of a measurement. We can only calculate the probabilities of different possible results. This is not because we are missing information. It is because the system itself does not have definite properties until it is measured. The mathematical tool used to describe quantum systems is the wave function. The wave function contains all the information that can be known about a system. But the wave function itself does not give direct values for observable quantities like position or momentum. Instead, the square of the wave function's amplitude at any point gives the probability density of finding the particle at that location. To find the actual probability, we integrate this density over the region of interest. This probabilistic interpretation was first proposed by Max Born in 1926 and is now called the Born rule. It is one of the key postulates of quantum mechanics. The Born rule connects the abstract mathematical wave function to the physical outcomes we observe in experiments. It tells us how to extract predictions from the theory, and those predictions are always in the form of probabilities. When a measurement is made, the wave function collapses, and one of the possible outcomes is realized. Which outcome occurs is fundamentally random. There is no hidden mechanism or deeper layer of reality that determines the result. Quantum mechanics is intrinsically probabilistic. This was deeply troubling to some of the founders of the theory, including Albert Einstein, who famously said that God does not play dice with the universe. Einstein believed that quantum mechanics was incomplete and that a more complete theory would restore determinism. However, decades of experiments have confirmed that quantum mechanics is correct and that the randomness is real. Tests of Bell's inequalities, for example, have shown that no local hidden variable theory can reproduce the predictions of quantum mechanics. The probabilities are not due to ignorance of hidden factors, but are built into the structure of reality. The probabilistic nature of quantum mechanics has profound implications. It means that identical systems prepared in exactly the same way can produce different outcomes when measured. If we repeat an experiment many times, we will see a distribution of results that matches the probabilities predicted by the wave function. Individual outcomes are unpredictable, but the statistical pattern is precise and reproducible. This does not mean that quantum mechanics is vague or imprecise. On the contrary, it is one of the most accurate theories in all of science. The predictions it makes about probabilities have been tested to extraordinary levels of precision and have always been confirmed. The theory is highly predictive, just not in the deterministic way that classical physics is. Probability in quantum mechanics also appears in the form of uncertainty relations. Heisenberg's uncertainty principle shows that there are limits to how precisely certain pairs of quantities can be known simultaneously. The position and momentum of a particle, for example, cannot both be measured exactly at the same time. This is not because our instruments are imperfect, but because the particle does not have exact values for both properties. The more precisely one is known, the more uncertain the other becomes. These uncertainties are reflected in the wave function. A wave function that is sharply peaked in position space is spread out in momentum space, and vice versa. The wave function encodes the probabilities for both position and momentum measurements, and the trade-off between the two is a direct consequence of the wave nature of particles. The role of probability extends to all aspects of quantum behavior. When a particle is in a superposition of states, each possible state has a probability amplitude. These amplitudes can interfere with each other, producing patterns that cannot be explained by classical probabilities. In classical probability, probabilities are always positive numbers that add together. But in quantum mechanics, probability amplitudes are complex numbers that can add or subtract, leading to interference effects. This interference is what produces the pattern seen in experiments like the double-slit experiment. Each path the particle could take has an associated probability amplitude. These amplitudes are added together, and the resulting combined amplitude is squared to get the final probability. Where the amplitudes add constructively, the probability is high, creating bright bands. Where they add destructively, the probability is low, creating dark bands. This is fundamentally different from how classical probabilities combine. The probabilistic nature of quantum mechanics raises deep philosophical questions. If outcomes are truly random, what does that mean for causality and the structure of reality? Can we say that a particle has properties before we measure them, or do those properties only come into existence at the moment of measurement? These questions have led to various interpretations of quantum mechanics, each offering a different perspective on the meaning of probability in the theory. Despite these interpretations, the practical use of probability in quantum mechanics is clear and consistent. Scientists and engineers use quantum probabilities to design technologies ranging from transistors and lasers to quantum computers and cryptographic systems. The probabilistic predictions are reliable, testable, and essential to modern technology. Probability also plays a central role in quantum field theory, the framework that extends quantum mechanics to include relativity and describes the interactions of particles and fields. In quantum field theory, particles are seen as excitations of underlying fields, and the probabilities of different interactions are calculated using sophisticated mathematical techniques. These calculations have produced some of the most precise predictions in physics, such as the magnetic moment of the electron, which agrees with experiments to more than 10 decimal places. In summary, probability is not just a tool for dealing with incomplete information in quantum mechanics. It is a fundamental aspect of how the quantum world works. The wave function encodes probabilities for all possible measurement outcomes, and those probabilities are intrinsic to the system. Quantum randomness is real and has been confirmed by countless experiments. Far from being a weakness, the probabilistic nature of quantum mechanics is one of its strengths, allowing it to make precise and testable predictions that have stood the test of time. Chapter 9. How quantum physics changed our view of reality. Quantum physics has fundamentally transformed how we understand the nature of reality. Before its development, the universe seemed predictable, mechanical, and governed by clear rules that could be understood through observation and reason. Classical physics painted a picture of a clockwork universe where every effect had a cause, and the future could be calculated from the present. Quantum mechanics shattered this view and replaced it with something far stranger and more subtle. One of the most significant changes brought by quantum physics is the realization that reality at the smallest scales is not deterministic. In the classical worldview, if we knew the exact state of every particle in the universe, we could in principle predict everything that would happen next. The future was already written in the present. But quantum mechanics tells us that this is not true. Even with perfect knowledge of a quantum system, we can only predict probabilities, not certainties. The future is not fixed but open to multiple possibilities that resolve only when measurements are made. This introduces a fundamentally probabilistic element into the fabric of nature. Randomness is not just a result of ignorance or complexity, but is woven into the very structure of reality. This was a difficult idea for many early physicists to accept. Albert Einstein, despite his contributions to quantum theory, never fully embraced this aspect of it. He believed that there must be some deeper level of reality where determinism is restored. But experiment after experiment has confirmed that quantum randomness is real and cannot be explained away by hidden variables. Quantum physics also changed our understanding of what it means for something to exist. In classical physics, objects have definite properties whether we observe them or not. A planet has a specific position and velocity at every moment, even if no one is looking. But in quantum mechanics, particles do not have definite properties until they are measured. Before measurement, they exist in superpositions of many possible states. The act of observation brings these properties into being, collapsing the wave function and selecting one outcome from many possibilities. This blurs the line between the observer and the observed. In classical physics, observation is passive. We look at the world and it reveals itself as it is. In quantum mechanics, observation is active. It shapes and determines the state of the system. This raises profound questions about the role of consciousness, measurement, and information in the structure of reality. Another way quantum physics changed our view is through the concept of wave-particle duality. Before quantum mechanics, waves and particles were seen as fundamentally different types of things. Waves were spread out, continuous, and could interfere with each other. Particles were localized, discrete, and followed definite paths. But quantum physics showed that this distinction breaks down at small scales. Light, which was thought to be a wave, also behaves like particles. Electrons, which were thought to be particles, also behave like waves. All matter and energy have both wave and particle characteristics, and which aspect we see depends on how we choose to observe. This duality forces us to give up the idea that physical objects are simply one thing or another. Instead, they are both, or neither, depending on the context. Reality is richer and more flexible than the rigid categories of classical thought allowed. The quantum world does not fit neatly into the boxes we create based on everyday experience. Entanglement adds another layer of strangeness. In classical physics, objects are separate and independent. What happens to one object does not instantly affect another unless there is some physical connection or signal between them. But quantum entanglement shows that particles can be connected in ways that transcend space. Measuring one particle instantly determines the state of another, no matter how far apart they are. This non-local connection has been confirmed in countless experiments and challenges our intuitions about space, separation, and independence. Einstein called this spooky action at a distance and saw it as evidence that quantum mechanics was incomplete. But the experiments that tested Bell's inequalities showed that entanglement is real and cannot be explained by local hidden variables. The universe is fundamentally non-local in a way that classical physics never imagined. This does not mean information travels faster than light, but it does mean that the quantum correlations between distant particles are real and immediate. The uncertainty principle changed our view of knowledge itself. In classical physics, the limits on what we can know are practical, not fundamental. Better instruments and more careful measurements can always improve our knowledge. But Heisenberg's uncertainty principle sets absolute limits on what can be known. Certain pairs of properties, like position and momentum, cannot both be precisely determined at the same time. This is not because of flaws in our tools, but because the properties themselves do not have exact values simultaneously. The universe has a built-in fuzziness that cannot be removed. This challenges the idea that the universe is fully knowable, even in principle. There are questions that cannot be answered, not because we lack the means, but because the questions themselves do not have definite answers. This has philosophical implications that reach beyond physics into questions about the nature of reality, truth, and knowledge. Quantum physics also introduced the idea that the act of measurement is a physical process with real consequences. In classical physics, measurement reveals what is already there. In quantum mechanics, measurement changes the system, collapsing the wave function and selecting one outcome. This has led to debates about what happens during measurement, what role consciousness plays, if any, and whether the wave function represents something real or just our knowledge. Different interpretations of quantum mechanics offer different answers. The Copenhagen interpretation treats measurement as a fundamental process that stands outside the normal rules of quantum evolution. The many worlds interpretation says that all possible outcomes occur in separate branches of reality. The pilot wave theory says that particles always have definite properties guided by an underlying wave. Each interpretation provides a different picture of reality, yet all make the same experimental predictions. This shows that quantum mechanics forces us to separate what we can observe from what we can say about underlying reality. The development of quantum physics also revealed that reality at small scales is quantized. Energy, angular momentum, and other properties come in discrete units rather than continuous ranges. This was unexpected and revolutionary. In classical physics, quantities can vary smoothly, but in the quantum world there are jumps and gaps. Electrons in atoms can only occupy certain energy levels. Light is emitted and absorbed in discrete packets. This quantization is responsible for the stability of matter, the structure of atoms, and the behavior of light. Quantum mechanics has shown that the universe operates on principles that are completely different from what we see in everyday life. The smooth, predictable, deterministic world of classical physics is an approximation that works well for large objects but breaks down at small scales. At the quantum level, reality is probabilistic, non-local, uncertain, and deeply interconnected. This new view of reality has not only changed physics, but has influenced philosophy, technology, and our broader understanding of the universe. It has forced scientists to rethink fundamental concepts like causality, determinism, and objectivity. It has led to technologies that would have been impossible without quantum mechanics, from semiconductors to lasers to quantum computers. Quantum physics reminds us that the universe is far stranger than we ever imagined. It does not conform to our intuitions, because those intuitions were formed by our experiences with large, slow-moving objects. But the microscopic world follows different rules, and understanding those rules has opened new frontiers of knowledge and possibility. The shift from classical to quantum thinking represents one of the greatest intellectual achievements in human history. It shows that science is not just about accumulating facts, but about being willing to challenge and revise our deepest assumptions about reality. Quantum mechanics is now more than a century old, yet it continues to surprise, challenge, and inspire. It stands as a testament to the power of human curiosity and the endless capacity of nature to reveal new wonders. Chapter 10: Quantum Theory in the Real World. Quantum theory is not just an abstract set of ideas confined to laboratories and textbooks. It is the foundation for much of the technology that shapes modern life. From the device you might be using to listen to this video to the lights illuminating your room, quantum mechanics plays a role. Understanding how quantum principles translate into practical applications shows just how deeply this theory is woven into the fabric of our everyday world. One of the most important applications of quantum physics is in semiconductors. Semiconductors are materials that can conduct electricity under certain conditions and block it under others. This behavior depends on the quantum properties of electrons moving through the material's atomic structure. By carefully controlling these properties, engineers create transistors, the basic building blocks of all modern electronics. Transistors act as switches and amplifiers, and billions of them are packed into the microchips that power computers, smartphones, and countless other devices. Without quantum mechanics, none of this technology would exist. The development of the laser is another direct result of quantum theory. Laser stands for light amplification by stimulated emission of radiation. The process relies on electrons in atoms jumping between quantized energy levels. When an electron drops from a higher energy level to a lower one, it emits a photon of light. In a laser, this process is carefully controlled so that many atoms emit photons in a coordinated way, producing a beam of light that is intense, focused, and coherent. Lasers are used in everything from barcode scanners and optical communications to surgery and scientific research. Magnetic resonance imaging, or MRI, is a medical technology that depends on quantum mechanics. MRI machines use the quantum property of nuclear spin to create detailed images of the inside of the human body. Hydrogen nuclei and water molecules act like tiny magnets. When placed in a strong magnetic field and exposed to radio waves, these nuclei absorb energy and then release it. The timing and intensity of this release depend on the surrounding tissue, allowing the machine to build up a detailed image. MRI has become an essential tool in diagnosing and monitoring a wide range of medical conditions. Quantum mechanics also explains the behavior of light-emitting diodes, or LEDs. LEDs produce light when electrons move across a junction in a semiconductor material and drop to a lower energy level, releasing photons. The color of the light depends on the energy difference between the levels, which is determined by the quantum properties of the material. LEDs are far more energy efficient than traditional light bulbs and have become the standard for lighting in homes, vehicles, and displays. Solar cells, which convert sunlight into electricity, are another application of quantum physics. When photons from the sun strike a solar cell, they can transfer their energy to electrons in a semiconductor, knocking them into a higher energy state and allowing them to flow as electric current. The efficiency of this process depends on the quantum interactions between light and matter. Advances in understanding these interactions have led to more efficient solar panels that are helping to provide clean, renewable energy. Quantum tunneling, a phenomenon where particles pass through barriers they classically shouldn't be able to cross, has practical uses as well. Flash memory in USB drives and solid-state hard drives relies on tunneling to move electrons into and out of storage cells. Scanning tunneling microscopes use tunneling to image surfaces at the atomic level, providing scientists with a powerful tool for studying materials and designing new technologies at the nanoscale. Atomic clocks, the most precise timekeeping devices ever built, depend on quantum mechanics. These clocks measure time based on the vibrations of atoms as they transition between energy levels. Because these transitions occur at very specific frequencies determined by the laws of quantum mechanics, atomic clocks are incredibly accurate. They are essential for GPS systems, which rely on precise timing to calculate positions. Without atomic clocks, GPS navigation would not be possible. Quantum cryptography is an emerging technology that uses the principles of quantum mechanics to create secure communication systems. One method, called quantum key distribution, uses entangled or superposed photons to transmit encryption keys. Any attempt to intercept the key disturbs the quantum state of the photons, alerting the users to the presence of an eavesdropper. This provides a level of security that is fundamentally guaranteed by the laws of physics, not just by the complexity of a code. Quantum computing is one of the most exciting and rapidly developing areas of quantum technology. Unlike classical computers, which use bits that are either 0 or 1, quantum computers use qubits that can be in superpositions of both states at once. This allows quantum computers to process vast amounts of information in parallel. While still in early stages of development, quantum computers have the potential to solve certain problems much faster than classical machines, including simulating complex quantum systems, optimizing large networks, and breaking certain types of encryption. Quantum sensors are being developed to measure physical quantities with unprecedented precision. By exploiting quantum properties like superposition and entanglement, these sensors can detect tiny changes in magnetic fields, gravity, or time. Potential applications include improved medical imaging, more sensitive detectors for gravitational waves, and better navigation systems that do not rely on GPS. Quantum mechanics is also essential to our understanding of chemistry. The way atoms bond to form molecules, the shapes of those molecules, and the reactions they undergo are all governed by quantum rules. The electrons in atoms occupy orbitals defined by quantum wave functions, and the overlap and interaction of these orbitals determine chemical properties. Modern chemistry and materials science rely heavily on quantum theory to predict and explain the behavior of substances. Even the stability of matter itself is a quantum phenomenon. In a classical world, electrons orbiting a nucleus would radiate energy and spiral inward, causing atoms to collapse. But quantum mechanics prevents this. The uncertainty principle and the quantization of energy levels keep electrons in stable orbitals. Without quantum mechanics, atoms as we know them could not exist, and neither could the molecules, materials, and life forms built from them. Quantum mechanics also plays a role in understanding and developing superconductors, materials that conduct electricity with zero resistance at very low temperatures. Superconductivity is a quantum phenomenon involving the formation of Cooper pairs, where electrons team up and move through the material without scattering. Superconductors are used in powerful magnets for MRI machines, particle accelerators, and experimental fusion reactors. The study of quantum mechanics continues to drive innovation. Researchers are exploring new materials, new forms of quantum computation, and new ways to manipulate and control quantum systems. Each discovery opens new possibilities for technology and deepens our understanding of the natural world. Quantum theory has also influenced fields beyond physics. It has shaped how we think about information, computation, and communication. Concepts from quantum mechanics have been applied to cryptography, optimization, and even machine learning. The quantum perspective offers new ways to approach problems that are difficult or impossible with classical methods. In daily life, we may not think about quantum mechanics, but it is there, quietly enabling the technologies we rely on. Every time we use a computer, turn on a light, take a photograph, or navigate with GPS, we are benefiting from principles that were discovered by exploring the behavior of the tiniest particles in the universe. Quantum theory reminds us that the most abstract and fundamental science often has the most practical and transformative applications. It shows that curiosity-driven research into the nature of reality can lead to innovations that change the world. The journey from understanding the photoelectric effect to building quantum computers is a testament to the power of science to not only explain the universe, but to reshape how we live in it. As technology continues to advance, quantum mechanics will play an even larger role. The next generation of computers, sensors, communication systems, and materials will all be built on quantum principles. Understanding these principles is not just important for physicists and engineers, but for anyone who wants to understand the world we live in and the future we are building. Quantum theory is one of the greatest achievements of human thought. It has revealed a universe far richer, stranger, and more beautiful than we ever imagined. And it has given us tools to explore, manipulate, and harness that universe in ways that continue to surprise and inspire. The quantum world is not separate from our everyday world. It is the foundation on which everything rests, and the more we learn about it, the more we discover about what is possible.